in Austin. And so I'm going to talk about some joint work with Cyril Lecuire, who's in Toulouse. And what I plan to do is to start rather slowly, because what I expected is that there would be students and well, I don't know. So please stop me if you want some information. I hope I'll be able to fill in the gaps. And okay, so let's start. So as I said, okay, it's rather slow, but it's working. So the general theme is about groups and geometry. So just let me remind you that when we have a Riemannian manifold, then we can consider its universal cover. And the fundamental group acts geometrically on the universal cover by isometries properly discontinuously and co-compactly. And we recover the manifold by looking at the quotient of the action. Okay. And so the central question of the talk is to try to answer to the question which groups can be the fundamental group of a compact manifold and in which dimension. Okay. And so the way I want to answer this problem is to use geometry group theory. Okay, and so since you've had several talks, I'll just remind you the definition of a quasi-isometry, but I don't really motivate the definition. Okay, so a quasi-isometry between two metric spaces is a bi-Lipschitz map up to an additive constant. And so what we understand is the large scale of the geometries of the spaces, but we don't care about what's local, but I guess you all know that. So here what I'm interested in is to define a notion of quasi-isometry for a group, and for this we consider locally finite Cayley graphs. And it turns out that there are always quasi-isometries to each other, so we can talk about the quasi-isometry class of a group by just considering one of the Cayley graphs. Okay, so I guess all this is pretty standard, right? Okay, so I'll go to the next slide. So there are two elementary examples of quasi-isometries that we cannot. So to the question of so the question that I will have is, if I have a group which is quasi-isometric to the fundamental group of a manifold, is it itself the fundamental group of a manifold of the same dimension? That's more or less what I want to go to. And for this, I cannot avoid two special cases that are the case of when I have a finite index subgroup, it is automatically quasi-isometric to the ambient group. And also, if I look at the quotient of a group by a finite group, it will be also quasi-isometric. So then I cannot distinguish a group from finite extensions and from finite quotients. So that these are two important examples. And what will be central to the talk is the Schwarz-Milnor lemma that I state as a theorem that says that the fundamental group inherits, in some sense, the geometry of the universal cover of the manifold. Okay, so can you hear me well and no problem with the slides? Okay. And so this will come into play during the whole talk, because the way we want to answer the question, we will deal case by case, and the geometry of the manifold of the group will be important for this. So the general program about geometry group theory is to classify finitely generated groups up to quasi-isometry, and then what we want to understand is, within a class, what does it contain? Okay, so as I said, we have to work up to elementary quasi-isometry, if I can say so. Okay. Ça va être dur, sorry. I'm at home, as you can imagine. And people hate it when I make Zoom talks. Okay. But since it's 7 p.m., I had to be home. Okay. So the question is, as I said, is which groups are quasi-isometric to the fundamental group of a compact three manifold? So of course, it's an interesting question because all groups are not fundamental groups of three manifolds. So the basic example is Z4. So there is a topological proof that it cannot be the fundamental group of a closed three manifold, where you look at the homological groups and it turns out that you get some counterexample. It's a little harder if you assume that you may have boundaries, but what I just wanted to say is that the question is relevant because we know that every group is not like that. Okay, so, and so the main theorem, if ever shows up, okay, thanks, is that if so it's the quasi-isometric rigidity of the class of three manifold groups. So it says that if I take any finitely generated group and I assume that it is quasi-isometric to the fundamental group of a compact three manifold, then it will contain a finite index group isomorphic to the fundamental group of a compact three manifold. Okay, so here there are two things I want to emphasize. Is first that I allow compact three manifolds with or without boundaries. And also, I don't need to look at finite quotients. So I can get rid of these elementary quasi-isometries, this class. And then it's a result of many people. And with Cyril Lecuire, we just added the last step to end the proof. So what I would like to explain is why do we stick to three manifolds and we don't consider the other cases? Essentially because it was already done. And what's the contribution of all these people? Because they are, without them, nothing would have been done. And maybe we did the easy parts, but since we're the last ones, I guess it was not completely true. You make up your own mind after that. Okay, so it's okay up to now? Okay. So, so then the theorem, the general theorem is known for in any dimension. Okay, so you fix any dimension, you look at a finitely generated group, you assume that it is quasi-isometric to the fundamental group of a compact manifold of any dimension, then it will contain a finite index group isomorphic to the fundamental group of the same dimension. Okay, so actually in dimension at least 4, it's not very difficult because then it was already known to them, so it's in the early 20th century, that any finitely presented group is the fundamental group of a compact manifold of any dimension. There are several proofs of that result. And the thing is that being finitely presented is a property that is preserved under quasi-isometries. And the fundamental group of a compact manifold is finitely presented. So then you just pack these things together. So then if I look at low, so it's really, the problem is interesting only in low dimension. And so in dimension 0, there's nothing to say because then the only manifold or connected manifold is a point, right? And so the fundamental group is trivial, so you only look at finite groups, and so there's nothing to say. Then for groups, for manifolds in one dimension, you have two cases. If you have boundary, then it's the interval that is simply connected, so there's nothing much interesting to say. And otherwise, it's the circle. So then you look at groups that are quasi-isometric to the cyclic group. And then this is a standard result. It's not very hard. It can be taught in a graduate course. It's rather reasonable, but still it's important to know it. And I guess it's due to studies. I don't exactly know because the language of quasi-isometries is, I guess, is, well, I don't know. The first time I've seen it in a paper, it was in a paper by Margolis from 70 or 71, where he extended Mosso's rigidity theorem to the way we state it today. But it's the same sort of period, I think. So now if I go to surface groups, then it becomes a real theorem. Okay, so finitely generated group quasi-isometric to the fundamental group of a compact surface contains a finite index subgroups isomorphic to the fundamental group of a compact surface. So then, as before, if the surface is simply connected, then there's nothing to say. If the surface is the torus, then the fundamental group is Z2. And there it's already a hard theorem to prove that. I don't know if you've seen it in your lectures, but the standard proof uses Gromov's polynomial growth theorem. And there is another proof that avoids it by Cornulier, Teixeira, and Valette. But I wouldn't say that it is that easy either. Okay, it requires a lot of material. So going to the cyclic group to Z2 is already a big step. And then if the surface has higher genus, then it can be endowed with a hyperbolic metric. And this is due to independently Gabay and Cassandre inverse in this generality. Because it's compact, I have to take care of the triangle groups. And this was not dealt by Touquet. It was the case that he could not deal with. So that's why he's not quoted, but of course, it's Touquet who started his story for surface groups, or groups acting on the circle. Okay. Oops. Something happened. I'm sorry, I don't know what's happened. Wait. I lost the connection on my iPad, I'm afraid. So did I come back?
Worries. You can, yeah, you can share your screen
yes,
again.
Okay.
Maybe.
So then I'll try to split the screen again. Oops. I'm sorry. I have to put on this. Oh no, that's okay, wait. Screen. I don't know where it stopped. Okay. Let me try to find okay.
Yeah. Looks
Great.
great. Go back. Yeah.
Oh. Yes. And so now the second case is when you have boundary. So what I wanted to say on the previous screen is that here it's really important. The uniformization theorem is really important for the proof. So each time it's a different proof. Well, for the S2, we don't care, but it's more for Z2 and the other cases. It's very specific to the geometry. And then when you have boundaries, so you still have cases that we've already seen. So the disk is simply connected, or you have an annulus, the fundamental group is cyclic. And all the other cases are finite. You must know that all the fundamental groups are free groups. And in this case, it follows from Stalin's that a group quasi-isometric to a free group is itself essentially free. Okay, so the hardest case were on the previous screen. And so the strategy to go to dimension 3 will use also the different geometries and the uniformization theorem for 3 manifolds. Okay. So I recall just the statement of the main theorem. And so what was known before we started is the case when well, at least the way it was stated is when you look at manifolds that are closed, orientable, and irreducible with 0 Euler characteristic. Okay, and so our input with Cyril Lecuire is to deal with Kleinian groups. Okay, so what I would like to do is first to explain what was. I'm sorry for that. Is to explain how the main steps, the main cases done by Gromov, Ponceau, Sullivan, etc. And then try to give some ingredients of the proof with Cyril for Kleinian groups. Okay, so first I will explain the terminology. So can I proceed? Is it still okay?
Sorry, what is the difference between the first two? Is the second one is only about zero Euler characteristic? Oh, I see. You're splitting it into two. Okay.
So the fact that it's orientable is not a problem, because in any case, when you have a manifold, you can always take the double cover. It remains in the same quasi-isometric class because it's a finite index.
Right. Okay.
And so there's nothing, but what is important is irreducible and zero Euler characteristic. And I will explain what it means in 3 dimensions.
Okay.
It's very specific. So first, so then, as I said, since we are interested only up to quasi-isometry, we can assume that the manifold is always orientable. And being irreducible means that each time you find a 2 sphere inside a manifold, it will bound a ball. Okay. So it's always the case, for instance, for hyperbolic 3 manifolds. They are always irreducible automatically. And then about Euler characteristic, so there are essentially two cases. When you have no boundary, then the Poincare duality will tell you that the Euler characteristic is always 0. And otherwise, if you want to compute it when you have boundary, the idea is to double it. And then you have a simple formula that relates the Euler characteristic of the manifold with its boundary. So you see that it's just 1/2 if I make the computation correctly. Okay, so meaning that so in the previous theorem, it asked that the manifold had 0 Euler characteristic. So it means that either the manifold is closed, so has no boundary, or it has a finite collection of tori on the boundary. Okay? And so what was left is when you have negative, so other sorts. So usually when you have 2 spheres on the boundary, you fill them up by balls. And so what's left is when you have, what was left was when you had some heterogeneous boundary. So we are interested in the Stosson's and Perelman uniformization theorem. So in particular, we're interested in what are called geometric manifolds. So in 2 dimensions, we know that we can always have a metric that has constant sectional curvature, but it's no more the case in higher dimension. So here, Thurston identified 8 different geometries in the sense that the metrics are homogeneous and that there exists a compact closed manifold. Okay, so here the 8 geometries. So you have those that have constant curvature like S3, E3, that is the Euclidean space, and also the hyperbolic space H3. Then you can have some mixture of different things like S2 cross R or H2 cross R. And then you have nil manifolds, so you can think of as the Heisenberg group with an invariant metric. You have the universal cover of PCL2R and the Sol manifold. Okay? So these make the 8 different geometries. And so of course, it would be too easy if the theorem said pick a compact manifold, then it admits one of these geometries that you can uniformize it like that. But it's not the case. But if you cut into pieces along spheres and tori, then and bring balls to these to the boundary spheres, then each piece can be geometric. So the idea is that you start with any orientable 3 manifold. You can split it so that it becomes irreducible. And then maybe you can split it a little more, and then each little piece will be geometric. Okay. And so this is a uniformization theorem in 3 dimensions. And so the theorem that I stated that was known before we started working on this project was known for all the geometric manifolds with that are closed or that have tori boundaries, and and the non-geometric ones also. And so it turns out that two of these geometries are quasi-isometric. So then we only need to deal with one. So H2 cross E1 and PSL2 twiddle. So this was it was known for a long time. I don't know exactly now. Okay, so what do I want to say about that to start with before saying who proved what? What is implicit in the statement is that we need a geometrization. Even though each case was proved before, I could not state the theorem like that before the uniformization theorem was known. And then when you have non-empty boundary, then you don't have too much choice actually on the geometry. So either it's Euclidean, or it's H2 cross R, or it's H3, hyperbolic. Okay. And when your manifold is non-geometric, then you can always make sure that each piece will be modeled on one of the two geometries that is either H3 or H2 cross R. So it's really boils down to very particular cases. Okay, can I continue?
Sorry, what, could you explain that last point? I'm confused. A non-geometric manifold?
So if you have a non-geometric manifold, that means that you have to use the Jsj decomposition for manifold.
Oh, and then you're saying its pieces have H2 cross R and H3.
Piece, then it will be either Seifert or hyperbolic. And when it's Seifert, you can put this H2 cross R.
Yeah, up to quasi-isometry.
Yes, exactly. Because
okay.
So there are some specific
to
do, but okay. So as usual, so S3 is simply connected, so there's nothing to say. S2 cross R, the fundamental group is essentially cyclic, so there's nothing to, it's already done. And then we come down to the hard stuff, if I can say so. So first, when the group has a polynomial growth, so you get either Euclidean structure or the nil manifold. And in this case, so Gromov tells you that this class is preserved, and the group is virtually nilpotent. But you need, I think, Ponsu tells you how to distinguish both geometries by looking at the asymptotic cone. So in the first case, you get R3, and the second case, you get the Heisenberg group with a Carnot-Kara-Theodori metric. Okay, and these two are not quasi-isometric, and that's how you distinguish the two. Okay, when it's hyperbolic, so there was work of Cannon-Cooper using Sullivan, but I'll come back to it a little later on. And when the manifold has cusps, then there is a strong theorem of Schwarz, which says that actually the groups are commensurable. So you pick a finitely generated group, quasi-isometric to a non-uniform lattice in PSL2C, and then both groups are commensurable. So they contain finite index subgroups that are isomorphic, up to finite quotients at the time, but then we are able to get rid of it. So the case of the Sol geometry is quite recent. It's due to Eskin, Fisher, and White, and it's also a very different proof than all the other ones. It relies on the machinery that they developed called the coarse differentiation. And so all these techniques are each time very different. Okay? And then the case of non-geometric manifolds was dealt by Kapovich and Led. And it's very efficient, and it applies also when you have a negative Euler characteristic. So really, for us, the only case that we really needed to work on was around Kleinian groups. And then we could use the machinery that was developed by Kapovich and Leb. Kapovich and Leb, so it's Misha Kapovich, just if you want to know which one of the three. And Kapovich and Leb also proved the quasi-isometric rigidity of H2 cross R in the same paper. But they acknowledge also the fact that it was done in Wiefel's thesis. Okay. So this is what was known before us. So as I said, what we did was to deal with Kleinian groups. So just in case you forgot a little bit what is a Kleinian group, so it's just not having slides. So I remind you the definition. So a Kleinian group is a subgroup, a discrete subgroup of PSL to C. Thanks to Zellberg lemma up to finite index, I can assume that it is torsion-free. And so, and since I'm working up to quasi-isometries, that's fine. And so what is interesting for Kleinian groups is, on the one hand, we can see them as acting by isometries on H3, properly discontinuously. And also, they define a conformal dynamical system by acting, by looking at them as acting by Möbius transformation on the Riemann sphere. Okay, so on the Riemann sphere, the action is not properly discontinuous in general, but we can split the sphere into two invariant sets, the ordinary set and the limit set. The ordinary set is the largest set where the action is properly discontinuous, and the limit set is where the things are happening from the dynamical point of view. Okay. And so what you can do also is to identify H3 with the unit ball in R3, identify the sphere with the boundary, the Riemann sphere with S2 by the stereographic projection. And then both actions that we have, actually they patch together into one action on the closed unit ball, okay, by Möbius transformations of the closed free ball. And then if we consider the action only on the ball and on the ordinary set, then the action is properly discontinuous and it's also free. And thus we can look at the quotient. It will be a good manifold, well behaved, that we call the Kleinian manifold. And the fundamental group of that manifold is exactly K. Okay, so this fits with a uniformization theorem. And that's why that's the case that was removed. Okay. And so the boundary, so if the manifold is closed, then the ordinary set will be empty. And the ordinary set amounts for the boundary of the manifold. Okay. So what we want to prove now is that if you have a finitely generated group that is quasi-isometric to any finitely generated Kleinian group, then your initial group contains a finite index subgroup that is isomorphic to a Kleinian group that is geometrically finite, in the sense that it has a compact part, and the non-compact part is a union of cusps that are homomorphic to the torus cusp R plus. So this is what we call geometrically finite Kleinian groups. So how does the proof, what is the strategy of the proof, the general thing? So we start with an abstract group. So I will assume it's torsion-free. It's just for simplification for the top. We can deal with it. It's not very important, but at least on a safer ground. And we have a quasi-isometry. And then we want to do something about that. So the first step is to pick up the right Kleinian group. So we have a Kleinian group, so it's a subgroup of PSL to C, but maybe so we can choose it in its isomorphic class to be already geometrically finite. So this follows from Thurston's uniformization theorem, and it is explained in Kapovich's book on where he gives all the proof of the Haken case for three manifolds. So I don't know exactly who proved it, but at least Kapovich knows how to prove it. Okay, so the idea is that, so you have one Kleinian group that is finitely generated. It can be very ugly, but then you change the group. It's still isomorphic, so it doesn't change the quasi-isometric class. But now it's much simpler because it is geometrically finite. And This means, since you've already seen talks about it, that the formula K is relatively hyperbolic. That was not known to start with somehow. So we improve already our knowledge just from the before beginning the proof. Okay, so this is the first step to do. It was already known. And so since the group is relatively hyperbolic and you have a quasi-isometry, and the peripheral subgroups are Z2s, so we know that themselves they are not relatively hyperbolic. Then Drutu and Sapir tell us that G has to be also relatively hyperbolic. And the peripheral subgroups are quasi-isometric to Z2s. And moreover, what we gain also is that our quasi-isometry is not anything about Cayley graphs. It also takes the peripheral subgroups to the peripheral subgroups. So we improve the quasi-isometry. It's just because now we have some, we can hang on the quasi-isometry because it maps the peripheral subgroups to themselves. So it's a marked quasi-isometry in some sense. And that's crucial in, for instance, for Schwarz theorem. That it's not just a quasi-isometry, because a quasi-isometry has nothing to do with the actions on the Cayley graphs, of course. But there we have something that at least we get some information from the quasi-isometry. Some more, it's improved. I think that this is really important, and this is what we're going to.
But it's the same. You don't need to change the Kleinian group at that step.
No,
it's the same group.
It's the same group.
So phi, if nothing is changed at this step, it just turns out that phi actually has these properties.
Exactly. Yeah,
okay.
It's for free. It comes from. It's for free. You need Carnelian.
Yeah.
But for us, it's for free.
Okay.
Can I also ask something about the first step?
Oh, sure.
What if we start with K being a Fuchsian representation of surface group? How do you do the change? It's kind of confusing. It's kind of confusing me.
But if it was already Fuchsian, then I would apply the Gabay Cassagnon-Grice.
Yeah, but I mean, is the theorem of Karpowicz and Thurston still true in that case? I mean, how can you change the ends to like torus?
If it's finitely generated, it's automatically
that counts, Joe. I mean, you put on the surfaces at infinity, and that's compact.
Yeah, I think you already get it for free. The only case is if you have a big group, a degenerate group where the.
Okay, so you're saying in that case we don't even need the ends. You just we get something compact. Okay.
Yeah, if it's Fuchsian, it's okay.
Yeah.
But if it's not Fuchsian, because it's a surface, so abstractly it's a surface group, but the limit set is a dendrite. Then you need to change to go to the surface case.
I see. Yeah. Thank you.
You would apply this this thing. Okay. So let me go to the next thing. Okay. So then. If it wants to change. Okay, thanks. I'm talking to the computer. I'm sorry. So one thing that that is very interesting is that you have your two groups are quasi-isometric with the same the relative structure which match together. So this means that their Bowditch boundaries are homomorphic. And even more, what you get is that you can look at a visual distance at infinity on the Bowditch boundary, and it turns out that the action is what we call a uniformly quasi-Möbius action. So a Möbius action is an action on the Riemann sphere that preserves the closed ratios. So here it's in a metric sense, meaning that we look at this metric cross ratio. But essentially, it tells us the same sort of information, that if the cross ratio is small, then it remains small along the orbit of the group. Okay, so then we can do some analytic to tools to try to work with this. And why is it interesting? It's because of a theorem of Sullivan that tells you that when you have a uniform Quasi-Möbius action on the Riemann sphere, then it is always conjugate to an action by Möbius. So this is true on dimension 2. Okay? And so this means that the cases that were dealt by Cannon, Cooper, and Schwartz, they follow by this theorem of Sullivan. So Schwartz proved more, okay? And Cannon and Cooper did also some stuff with when you have cusps, but it was presented in a different way. But the fact, so the idea in the relatively hyperbolic case is to glue in Hall balls on the Z2s to reconstruct H3 in some sense.
Sorry.
So, yes.
And how much generality does that theorem of Sullivan hold? Like what kinds of groups, like and what kinds of limit sets can?
It's on the Riemann sphere, you need nothing. Just what is written. A uniformly Quasi-Möbius group is always conjugate, but it is finitely generated or not.
But it's on the Riemann sphere specifically.
Yeah. So if you go to higher dimension, then there's been some extension by Tukia. And so you need somehow to have enough conical points. So the conical points have positive measure. Because here, what's used by Sullivan is the measurable Riemann mapping theorem on quasi-conformal maps. And we know how to solve this equation only in dimension 2. And it does not hold in higher dimension. Because already the equation is nonlinear. And it's a mess. And then you need, so the proof of Tukia really uses dynamics, whereas here Sullivan relies on, he finds an almost complex structure that is preserved by the Quasi-Möbius group, by the group of quasi-conformal maps. So here he uses the fact that it is uniformly quasi-conformal. And then he applies this measurable Riemann mapping theorem. And then it's done. Whereas in higher dimension, you need to make a blow-up argument. And this is where you use the fact that you have enough conical points to take a point of density where you have differentiability. So it cannot hold in higher dimension. But then you have something similar also for Carnot-Kara-Theodori stuff. So this is a theorem of Cho, I think. So if you have a uniform quasi-conformal group acting on some Carnot-Kara-Theodori metric manifold with enough conical points, then it will be conjugated to a group of conformal maps. Other questions at this stage?
Maybe this is elementary, but is it true in general that if you have a quasi-isometry to a relatively hyperbolic group, you get some action on the Bowditch boundary? Is that true in general?
Well,
I mean,
well, you need the peripheral structures to match.
Okay.
Okay. Is to glue in the same. So if the peripheral structures are mapped one to the other by the quasi-isometry, then when you glue in the whole balls, you can do it on both sides simultaneously, and then you extend the quasi-isometry to the new space with the new whole balls.
Okay.
And hyperbolic, and then it's okay.
Okay, so if you have a group that's a quasi-isometry to a hyperbolic group, for example, the most basic case, I guess, then you do get an action on the boundary, even though it's not a homomorphism, right? It's just a quasi-isometry, but you still get an action on the boundary. Maybe this is elementary stuff. But...
Well, yes, because since the group is word hyperbolic, then your former group has to be word hyperbolic as well, right?
Yeah.
So then both boundaries are homomorphic.
Okay, yeah.
Okay. Somehow.
Okay.
No, the problems that come in is really to make sure that the peripheral structures are coincide, and this is not the case in general.
Okay.
Especially if you have parts that you have to clean them up to get really the minimal to have minimal parabolics.
I see.
So then the first idea that we could have is to say, I want to use this theorem of Sullivan. So I already have an action that is uniformly quasi-Möbius on the limit set. I just to fill in the action on the whole sphere and apply Sullivan theorem. So of course, there's no way we can proceed that way in general, because you have infinitely many components of the ordinary set in general. And you don't know if even if an element of the group extends as a homomorphism of the two sphere. This even is not, it's not always true actually, because the way the boundary is, the limit set or the Bodish boundary of the group G is embedded in the two sphere might not respect the topology of what is needed to extend something. So there are some in the paper of Kapovich and Kleinian on one-dimensional word hyperbolic groups. They have an example where it's the case. So the group is up to finite index Kleinian group, but it is not itself a Kleinian group, because well, it's not because, but one of the reasons is that in any case, every element does not extend as a homomorphism. And so then extending all the group action to a group action on the whole sphere and being uniformly quasi-Möbius, this is hopeless. Or at least I would never believe a proof like that, because it would be too messy. And so we have to get some other strategy. Okay? And one of the problems, as I try to, is that we don't get enough information from the quasi-isometry in general. So let me start again with my quasi-isometry. So the idea will be to split the groups and split in some sense, the quasi-isometry, to localize it in some sense. So that I get to the same setting as before, saying that not only I have some quasi-isometries between subgroups, but also I have some markings that is preserved, exactly like in the case of Schwarz, where I had his cusps, the Z2s that were mapped to each other. And so in some sense, it's a way of improving the quasi-isometry by localizing it in one way or another. Okay, so this is where the Jsj decomposition will come in. Since you've seen it already in previous weeks, I already give you some, I'll tell you as part of what's going to follow. No suspense for that one. Okay. So that's the idea, is you have your quasi-isometry, you try to get to split the action, split the quasi-isometry to improve the quasi-isometry, and then to get more information to be able to work. And this will make the strategy work compared to what the previous strategy looking at the action at infinity, because we will have more information than just a stupid homomorphism that will make the Bodish boundaries coincide. So once we have that, so we have this Best-Serre theory, we have all these vertex groups that match to each other, because you have the same action, an action of both groups on the same tree. And for each vertex, we have a quasi-isometry, and the edge groups match to each other up to bounded constants, distance, etc. And then what we want to prove is that each of these vertices, using the fact that we also have this improvement with edge groups, to prove that in this situation, I know how to prove that it is Kleinian, up to finite index. Once I know that these things are Kleinian, I will use my graph of group structure to say, well, I have all these Kleinian manifolds, I glue them together on the boundaries, and then I find a manifold with the right fundamental group. And once I have that, I apply Thurston's uniformization theorem, because my manifold was Haken in any case, so I don't need Perelman anymore. Okay, so this is the general strategy. So of course, the fact that the group GV is only virtually Kleinian means that it's not true that I can build a 3 manifold out of them. I don't know if the edge groups are really given by annuli or stuff like that. So here there's work to do. Between step 2 and step 3, there's something that is hidden. And in step 1, of course, there are things to be done. So okay, so it's not, but that's the basic idea. That's where we started from.
Sorry, what example should we have in mind here? So, I mean, K is already Kleinian, but you want it to split up further. What? Sorry, say again.
I will give you the example of a Kerkovich and Kleiner.
Okay.
What I do is they start with a torus and they make 2 holes on the torus. And they do 1 hole on the other by wrapping it twice on the second one.
Okay. Yeah.
Okay, so it's hard to, okay, maybe like this.
Okay.
And so it turns out that the group that you obtain is the torsion-free, word hyperbolic. The boundary is planar. But the group itself cannot be a 3 manifold group because of this wrapping, because of this element that wraps it twice. And on the sphere at infinity, what it does is that it switches 2 components like that.
Okay.
It's not an involution because it's torsion free, but it switches 2 components of the axis along the axis. And so the action cannot be extended to the whole thing. But then using the Jsj, what you will see is that the torus is a free group. Because you have the 2 holes, you get a free group with the 2 cyclic groups that are marked. And you can work with this to use afterwards a Gabay and stuff like that and find a finite index of it. Or here you can even use a 2-dimensional topology and orbifold stuff to find the cover. That's how they do in their paper.
Oh, okay. I see. Okay, so you find this splitting and
just splitting in general.
And then the point is you have some weird behavior like this, but using the splitting, you can sort of glue it back together in some finite index way to get rid of that or something. Is that what the point?
So what I was planning to do is to explain a little bit, give more details on each step.
Okay. Thanks.
So maybe question. So first, so the idea, so there are 2 cases I should consider. First is when you have splittings over finite groups, but this I will skip. Okay, the strategy is the same. Is essentially the same, so it doesn't matter. But I want to look at the Jsj decomposition along a line. That is maybe richer. Okay, so when you start with your Kleinian manifold, you can cut it into pieces. And each piece is, so here I'm trying to explain the first step, how the quasi-isometry, why the quasi-isometry can be localized. So when you do this topological Jsj decomposition, so I don't know if you've seen it before looking at Bodich's decomposition, but Bodich is somehow the algebraic version of that one. I hope you'll recognize it because that's okay. So there are several cases that can appear. You can have a solid torus. So this corresponds to the cyclic vertices in the Bodich's Jsj. Then you have the thickened torus because you can have some, this gives the cusps. So this does not exist in Bodich's thing because he only works with word hyperbolic groups. Then you have the thickened surfaces with holes that gives you some, so it's a surface and the annuli are given by the boundary components times the interval. And then you have the complicated pieces that are called the asymmetrical manifold. So is it okay with this decomposition? You've already seen it maybe, I don't know, okay. So then you can look at the action on the Basser tree that comes from this decomposition. okay, for the Kleinian group. And what we know is that each edge group has to be isomorphic to a cyclic group because it corresponds to the analyte along which you get your manifold. Okay, so it turns out that this decomposition can be read just from the topology of the limit set. And this is exactly what Bodic tells us, at least for word hyperbolic groups. And this was after extended to relatively hyperbolic groups by Groth and also by Hallmark and Ruska. But the basic ideas were already in this thing. And so Lecuire and Walsh, they really worked on the relationship between the algebraic Jsj and the topological Jsj to make the correspondence between the two. And so the edge groups correspond essentially to cut points or to local cut points. And that's why you can see them on the limit set. And so since both Bodic boundaries coincide, because they have the same peripheral structures to start with, it means that the local cut points are the same also. So you get the same Basser tree. Okay, so the topological and the algebraic Jsj decomposition, if I can say so, they match. And that's how you get this splitting of the global quasi-isometry vertices to vertices, and it match edge groups to edge groups because it matches the limit sets to the limit sets. Because that's how you build the thing. So there's a little work, but it's not very difficult. Because just to make sure that when you have the extension of a quasi-isometry to the limit sets, it extends really as a quasi-isometry on their convex fields in some sense. And that's what is behind. So it's a little harder because you have some parabolic groups, but otherwise you just work out the thing. But here now we have better quasi-isometries because we have all this additive structure, and these are cyclic groups, so we could not see them before because they were hidden in the Cayley graph. Okay, so now we improved our problem of taking any quasi-isometry between two groups by looking at a quasi-isometry which will preserve some cyclic groups, that will match some cyclic groups together. And this is very important. So this is essentially the idea behind the step one of the splitting of the Jsj. And so for step two, I want to focus on the paired asymmetrical manifolds because this is the harder case. The other cases were either cyclic, Z2s, or virtually free. And so we almost know how to deal with them. But with the hardest case, I guess, is that one. So what people do in low-dimensional hyperbolic geometry when you have a paired manifold, so this means that you have your manifold with some annuli on the boundary that are marked, and it's a maximal collection of annuli, so you cannot find another annulus properly embedded in your manifold to split it further. That is exactly like in Bodic's rigid stuff. What people do is that they pinch the core of each annulus. This you can do it geometrically, so that in the end you get you still get a geometrically finite group. But what you did is you transformed all the cyclic groups into parabolic groups, rank one parabolic groups. And so on the limit set, what you did is you have the two fixed points of the cyclic subgroups that are now matched together. And that's why the limit set that you obtain, if you do it well using so Thurston stuff, you get what some people call a Schottky set. So it's really the complement of round disks, pairwise disjoint round disks, like a Sierpinski carpet. Okay, so it corresponds to a three manifold with totally geodesic boundary. Okay. And so why is it? Oops, I'm afraid my Zoom stopped again. So I'm sorry, I have to reconnect my pad. I don't know why it's doing that all the time. Okay. Okay. But you're not there anymore, right? Ah, yes. Okay. Sorry. bring this thing up. Okay, good. Up. Okay, so why is this interesting? Is that because we pinch the edge groups and the edge groups corresponded in both cases, we can do it also for our initial group, our abstract group G. And then we get also an action of the vertex groups on this new limit set. And it remains also quasi-mobius. Because, so it's always the idea of gluing up whole balls in the right way and making sure that all the structure is preserved. But this is where we use the fact that the edge groups are mapped to the edge groups. So this is where the new ingredient that we obtain is bringing us something interesting. Okay. And then we have this great theorem, at least for us, for this problem by Bon, Kleinian, and Merenkoff, that said that when you have a Schottky set of measure 0, any quasi-Möbius map is a restriction of a Möbius map. So there's nothing to be done, actually. Our group GV is already Möbius by looking at its action on this new limit set. It comes almost for free. And we know that it has measure 0. I don't need the Alfors conjecture. It's just because it's geometrically finite. So this was already known for a long time. Okay. And so once we have that, we can unpinch the curves. So our group GV is already Kleinian. That action is already Kleinian, but it's not the right action because we change the Bodish boundary by pinching the pairs of points. So then we unpinch, and this we can do it because Thurston did all the theory that we need for that. And now we have our vertex group GV is now isomorphic to a Kleinian group, at least with the right Bodish boundary that is the same as before. So this is the step 2 that I explained before. So there's some sort of miracle coming in here. Okay, so it's 8:30, so I should maybe go a little further. So I don't know how much time you want to. I have 5 minutes to explain quickly what's left. And, so now the idea is that we have these manifolds and we want to glue them together. But as I explained before, it's not clear at all that the edge groups correspond to annuli and that the core are really, the generators are primitive simple closed curve, correspond to primitive simple closed curve. So it's not clear at all what's going to happen. So the new ingredient that we need is the notion of separability. Okay, so this should remind you stuff by work of Wise and all that. And so we don't use explicitly cat-0 cube complexes, but of course we've been very much inspired because for the geometrically finite cases, it was not that easy to make sure that. And in any case, our group is a mixture of everything, so it requires something a little different. And so what's important is that the obstructions to get manifolds with a simple closed curve represented by the edge groups is given by a finite amount of obstructions. And so this is really the core to the thing. And so the idea that is behind that I find really nice. So this is what Wise explained it to me how to do that. So the idea, you have this graph of groups, and what you do is you take a quotient vertex by vertex, and you make sure that the subgroups that you take match on the edge groups. And this is where you need the separability to do that. And then you have a quotient on graph of groups. And so here the idea is to get a quotient on a finite group, a finite graph of finite groups. So if you do it properly, then this thing is, we know it is virtually free because this was done by Scott and Wall. And we know that virtually free groups are locally, that every finitely generated group is separable. And then we can go back and lift up the things to work on our initial ambient group. So this idea that I did not know is working group by group. So we don't work on the Basser tree, but really on the graph of groups. And I think that's amusing, and it can be handy for other situations. But that's why I wanted to say little words about that. This idea of, so what you want is that when you pick your finite index subgroups on each side, you make sure that they match on the edge groups. So there's a little work, of course, and you need some non-trivial stuff, but since we already know that our groups are virtually Kleinian on each vertex groups, we know that they are rough by 8 order. And this gives us all the ingredients that are needed to find a finite index subgroup that will be really a manifold group. And then you just okay, you take the kernel of what you get rid of everything of the finite obstructions by using the separability on your virtually free group, and then you lift it back to your group and get group. And once you have that, then you can build your manifold, and you're done. And then you apply Thurston's theorem. Okay, so I was very quick in the end, maybe before also, but I'm sorry, and thank you for your attention.
Yes, thank you. Are there any questions? When you say those a finite set of obstructions, are they elements of some finite groups? Is that what you mean?
Yes. So, for instance, the kind of obstructions. So, what you want to make sure, for instance, is that the edge groups are primitive in each vertex group.
Right.
And this is not obvious. So this, you know how to, and also there was this example, in the example of Kapovich and Kleiner, there was these two, when you match these two things, this element of order 2 that was, it was not an element of order 2, but the curve that was wrapped twice along the other boundary,
yeah.
It was giving you an element that you wanted to get rid of. Okay, and so this is this kind of thing that you want to get rid of. And so then you use the separability of the vertex groups. And we have enough information because the way that search for each vertex, either it is Kleinian and you understand it well, or it is Z2. And when it's Z2, virtually Z2, then you have, you know also that you have a lot of separability.
Yeah.
And so this enables to take finite index subgroups on both sides and make them match. Sorry. And we use some sort of den fillings to do that for the when you have negative curvature. So the Kleinian groups that are not Z2s, because of course the Z2 is also a Kleinian group if you want. But I mean, when you have negative curvature, then you can use some den fillings, abstract den fillings that will the same sort of strategy as I explained when you make these quotients to vertex by vertex to be able to find a finite index subgroups where you control the edge groups, the new edge groups.
Okay. Thanks.
So is there some, how much about Kleinian are we really using here? If you have is there some more general statement you can make about if there's a splitting where you have separability in each piece or something and some other assumptions you could do this or?
Yeah, exactly. So in our paper, we have a general statement in that way. So we have a splitting along two where the vertices are of two different classes. One is where you can do some deep den fillings in such a way that the quotient is residually finite. And the other sort of vertex groups have to be, you have to have many separable subgroups inside.
Okay.
And
so
then what you add also is that the second category where you don't have a very good control actually, is that it's only on one side of an edge. So the second kind are not do not correspond to each other with an edge. Whereas the first kind, we don't care. Because the first kind, we can do something very precise. So the first kind is what we use with negative curvature. We have the assumptions coming from negative curvature. The second sort is what corresponds to the Z2s. But it's a little messy, or virtually Z2s, which is a little messy to find really the edge rules that we want. But with the first one, we really can pick up the edge rules.
I see.
I can give you some more. I have the paper close to me, so I can give you a more precise statement, but maybe.
Oh, it's okay. It's okay. Yeah.
It's a little complicated.
Well, it seems like a general technique
along those lines.
Mm-hmm.
I don't know if we tried to look for the right notion. I don't know if it's the correct one, but at least it's rather general and it applies to our case.
Cool. That's very nice.
Thank you.
I'm sorry, I'm 10 minutes late to a meeting. Thank you very much. I have to run, but don't let me stop others from asking questions. It's good to see you, Peter.
Bye-bye. So I don't know, maybe I should put, so here it's getting dark, it's 8:30. I'm going to put the light on. I don't know if you have any further questions or comments.
If there are no further questions, let's thank Peter again.
Thank you.
Thanks.
Nice talk.
Thanks.
I hope I didn't go too fast, and that you could still follow at least the basic ideas and ingredients.
Great.
Okay. I don't know if this one, oops, so I closed that one.
Yeah, thank you very much for explaining this interesting result.
Well, thank you. It was very nice having the opportunity to talk with you. I don't know why it's still out of Zoom. I think, oh yes, okay.